Helium, a gas discovered on the sun, is being used to test vehicles that will someday explore the universe in our race for space. Wind tunnel testing of space vehicles is only one of the many modern uses of helium. This is Science in Action. One of the most fascinating substances found in the Earth is a gas called helium. Now, it's the head of a family of 6 similar gases. The helium group, also known as the noble gases or the inert gases, and of this group, of course, helium is probably capable of the most diverse uses. These range all the way from arc welding to space-age technology. To tell us about this very interesting substance, we have prevailed upon the editor and the principal author of this 2-volume definitive work, Argon, Helium, and the Rare Gases. Actually, he's the assistant manager of the research laboratory of Linde Division of Union Carbide Corporation, located at Tonawanda near Buffalo, New York. And it's my pleasure to welcome Dr. Gerhard Cook. Gerhard, how have you been?
Just fine, thank you, Earl. It's a pleasure to be here.
Well, we're very glad to have you here, and if we're to learn about helium, I think we should start with something that I've always wanted to do, and that is work with balloons. A weather balloon in this case, and it's tied up above this helium cylinder. I'd like to lead off by asking you how much helium we have going into weather work at the present time.
Well, 7% of all the helium used last year in the United States went into aerology, which means the science of studying the atmosphere.
How does this compare with the use of helium for lighter-than-air craft in the early days?
Well, the production of helium in the early days was very small. The idea first occurred to somebody in 1917 that we should use helium to blow up lighter-than-air craft, balloons, and so on. And so the Bureau of Mines started trying to separate it from natural gas in Texas. The first liter, or the first cubic foot, cost them $2,000.
$2,000, fantastic.
But then they asked Linde Company to build them a full-scale plant. 4 years later, in 1921, this plant was operating, and they started filling Navy lighter-than-air craft. The Navy experimented with many different sizes of airships. They carried this all the way until 1935, always filling bigger and bigger ships. But the big ships offered so much resistance to the wind that when a hurricane came, it destroyed them, and the Navy finally decided to give up these very large ships. But we still use a lot of helium in balloons for studying the weather and occasionally to send a man up high for observations.
I'd like to move on now, Gerhard, to something else that I know very little about, and it's a special kind of torch. It's not an oxyacetylene torch, but a torch that makes use of helium. How does this work?
Yes, there are some metals which are not welded very well with the oxyacetylene process. When you try to use that process, the weld is poor, there's a lot of oxidation by the air and so on. These metals are especially the ones that are important in airplane manufacture, like aluminum, magnesium, and stainless steel. So this welding process was developed in which an electric arc supplies the heat. A stream of helium or argon comes through this tube here, flows out through this cup around a tungsten electrode. And when the welder wants to strike the arc, he just touches the tungsten electrode to the metal that's being welded. The arc begins, and he feeds in the welding rod with his other hand. And he keeps melting the metal and moving the torch along.
Let's see, you also use helium in such things as refining reactive metals.
Yes. You usually have to heat a metal in order to shape it or to refine it. And some metal there, again, if you do it in the air, they oxidize, lose their strength, so on. Especially such metals as titanium, zirconium, plutonium, uranium. They all have to be heated in an inert atmosphere, and either helium or argon is used for that purpose.
Gerhard, we've done a number of programs on rocket engines and rocket fuels and all this sort of thing, and yet we have never discussed the relationship of helium to the liquid rocket engine. How does this work?
Well, I think one reason that you haven't discussed it before is it's quite new. We now have these very large liquid-fueled rockets, and the liquid fuel has to be pushed out by something, and that's where the helium comes in. The helium is on the rockets in small tanks under pressure, and when they're ready to start the rocket up, the helium is fed into the top of the rocket, pushes the fuel down. The liquid oxygen comes in from another tank. the fuel and the oxygen get together and burn, and the products of combustion go streaming out of the bottom. That's what makes the thrust that boosts these rockets up. There's another use for that helium, and that is this. You know, a rocket has to be built of the lightest possible material, and the tanks in which the liquid fuel and the liquid oxygen are kept are made of very thin, flimsy stainless steel. So
Yes.
flimsy they would collapse when the liquid ran out if it weren't that the helium was holding the walls up.
Gerhard, I'd like to go now to something that faces every beginning student the first time they walk into that high school class in chemistry, over here.
Fine.
This, of course, is the periodic table, and everything that we know anything about as far as elements are concerned are on the table. Now, for our purposes, the only thing that we're interested in is the one that's indicated here, to begin with anyway, He, helium.
Yes, helium is the first member of the helium family of elements. It's called group 0 because there are 0 electrons outside the nucleus of these elements here, which are available for reacting chemically with any of the other elements. So they're chemically inert. The members of the group are helium, neon, argon, krypton, xenon, and radon.
How was helium first discovered, Gerhard?
Well, interestingly enough, helium was first discovered on the sun and not on the Earth. And it was discovered by spectroscopists who had learned that every element, when heated or agitated, gives off a characteristic radiation at a certain wavelength. And when there was a total eclipse of the sun in 1894, they discovered a line that they had never found before for any of the elements on the Earth. Next day, they again looked at all the spectra of the elements that they knew on Earth, and they still didn't find any. They decided they must have a new element. And they called it helium from the Greek word helios, meaning the sun.
So that then was the beginning of helium and the helium group as far as we're concerned.
Yes, it was a good many years later, though, before helium was found on Earth. And actually, the first element that was found on Earth from this family was argon, which was obtained from a sample of liquid air by Sir William Ramsay in England.
I'd like to ask you a little bit, Gerhard, about the availability of helium. Where are our helium stocks at the present time?
Well, most of the helium in the world comes from a few natural gas wells in the vicinity of Amarillo, Texas and 3 neighboring states. The helium exists in this natural gas to the extent of 1 to 8%.
Now, the Texans, or I should say the United States, then has somewhat of a monopoly on helium.
Well, we think that Russia has some helium, but they don't say much about it. And also there are some wells containing helium in Canada and in South Africa, but in neither of those countries is any of helium being recovered yet, although we think it will be before long. At the present time, the world depends, except Russia, depends on the United States for its source of helium.
I'd like to go back to our other section here and find out a little bit about the processing. Let's go over
All
here.
right. Well, Earl, getting natural gas that has helium in it out of the ground is no different from getting natural gas out that doesn't have helium. You just drill a hole in the ground, put a casing in, the gas comes up and you pipe it away.
That sounds rather simple, but then you have to get the helium out of the gas.
That's right. That is actually simple in principle, too. You liquefy all the gas except the helium. The helium is the hardest of all gases to liquefy, so what you do is liquefy the rest, separate the helium, and take the liquid natural gas away, re-vaporize it, and put it back in the gas lines. You have your helium.
One thing that I was interested in was this new method of, permeable membranes, whereby you're unable to get helium with something like this?
Yes, this is not a method that we've perfected yet, but it's interesting because this thin Teflon membrane that we have around here, that's only helium atoms through and no other molecules. So we're hoping to be able to fix a method whereby we just pass the natural gas over the membrane, the helium goes through, and the rest of the gas passes by.
Suppose that one of your consumers should say, well, I don't want gaseous helium, I want a liquid helium. Are there problems there?
Yes, we already have several such consumers, and we recently opened a plant at Amarillo, Texas, in which we take the helium gas from the Bureau of Mines, liquefy it, and ship the helium all over the United States in liquid form. Now, helium is the hardest of all gases to liquefy, as I mentioned before. If you try to treat it like air, which is just to compress it, expand it through a nozzle, it heats up instead of cooling down.
Shouldn't do that.
We have to do something else. So what we do all the usual that we do with air. That's we compress it, pass it through heat exchangers, But then we make it do work in an engine, an expansion engine, and that does cool the helium down. Then
That's the trick.
Yes, that's the trick. Then we pass that cold helium back around. We get the helium colder and colder by heat exchange. And then, when we get below the temperature of 51 degrees absolute, helium will cool when it's passed through a nozzle. And when we get the temperature way down below 7 degrees absolute, it'll cool all the way to a liquid. And we start getting some liquid drops. And then finally, when we get down to 4 degrees absolute, we have our liquid. That's the boiling point of liquid helium.
Well, take me around through this very quickly again now. It starts, first of all, what kind of a chamber do you go in?
Starts with compression. This is always the way these liquefaction cycles start. You compress it, and when you compress a gas, it gets hot, so you have to take that out with just ordinary cooling water. So you're back about room temperature. Then you start passing it through a series of heat exchangers. You get the cold helium, as I said, from later on in the cycle, so we won't go into that further. You pass it through a silica gel trap to take out the last of the impurities in the helium, because you don't want to clog the nozzle or anything further along.
Yes.
Then through some more heat exchangers, one at a time, until you get to this expander we already explained.
Yes.
And from the expander you go on through some more heat exchangers, and finally you get to the Joule-Thomson expansion nozzle, where the cooling takes place.
Well, the most fascinating part of this whole thing was the fact that you have to have special insulation, or otherwise you lose all of your helium. And I can't wait for the time when this kind of insulation will be available to the rest of us on the common market.
Well, Earl, the way this has to be prepared is so expensive, I don't think it's going to be available on the common market, although it's interesting to know that if you could insulate an ordinary thermos bottle of coffee with this, the coffee would stay hot for 100 years.
Yeah, I think what it would taste like, though.
Yes. Well, what this is, we call it super insulation, is the new insulation that's needed to keep the liquid helium off from boiling away when we ship it around to the customers. If we use the same insulation we used for liquid oxygen, liquid nitrogen, or liquid argon, it would hardly last a day with liquid helium. So we have this new insulation in which we have 70 layers of thin aluminum foil per inch spaced with thin layers of glass paper. Now, you remember that there's 3 ways that heat can leak into containers. They're convection, conduction, and radiation. We take care of all 3. We take care of the convection by evacuating the space to a very good vacuum, so there's just nothing to convect.
Yes.
We take care of conduction by having these very poor conducting glass paper. We take care of the radiation by having these aluminum layers from which the light is reflected and any radiation is reflected.
70 layers to an inch, and all of
That's
this inside of a vacuum. Well, if you have a
Right.
vacuum surrounding all this, then you must have good methods to test that vacuum to make sure you have no leaks in it.
Yes, we do, and one of the best ones involves the use of helium. Supposing that we have a large tank that we want to test for leaks. Most of the tank is made of sheet iron or steel, which we know has no leaks, but the welds are always suspect.
Yes.
So what we do, we start pumping out the tank with a vacuum pump, and we run part of the gas through a mass spectrometer which can detect helium before it gets the vacuum pump. So we keep pumping, and then we start playing a small stream of helium on the weld, very slowly. The minute we detect any helium in the mass spectrometer, we stop, because we know that's where the leak in the weld is.
And that's where the hole is.
That's right.
I see how that's done. I think we should move on now, Gerhard, to another very interesting field, and that has to do with this space simulation over in this next section. Let's move over here.
Yes, sir. You know, Earl, during the next few years, the federal government is going to spend about $65 billion to put a man on the moon. In order to do this safely, there's a lot we have to learn about outer space. And this is being done partly in space simulation chambers.
Yes.
About 200 of them are being built in various parts of the United States, some of them as large as 200 feet in diameter. Now, since there's an almost perfect vacuum in outer space, these chambers have to be pumped out. And they are pumped out mostly by the use of vacuum and diffusion pumps, but there's always a little gas left from those processes, and that has to be pumped out too. We have been working on a process which represents the best and the cheapest way of getting that last little bit of gas out, and I want to demonstrate the principle. We absorb out the last of those gases at a low temperature. We put a little type 5A molecular sieve, which is a type of synthetic zeolite, in the test tube. Put this pressure gauge on. This shows either pressure or vacuum. When it shows 0, it means it's just ordinary atmospheric pressure. Now I'm going to cool this molecular sieve down with liquid nitrogen. Now that's far from the absolute zero, but it will show that there's a large pressure drop because the molecular sieve can take out air even at that temperature. If we had liquid helium instead of liquid nitrogen, then we would get an even greater pressure drop.
I see the needle is moving.
Yes, the needle starts moving right away, and of course moves more and more as the air in there is absorbed.
This looks to me as though this might be a rather inexpensive way of handling these pressure chambers.
Yes, it is.
Now, will that take most
Now
of the
you
air
see,
out of there?
It'll take most of the air, all but the last little bit. And in fact, this pressure gauge here wouldn't even be suitable for showing the pressures left after if we held this in for long enough. So we'd have to have a very sophisticated type of pressure gauge if we had liquid helium here to show the end result. But you see
We're using nitrogen, but normally you would use helium for this.
Yes, yes.
Well, that's a very nice demonstration of how this can be done. You know, recently I saw some write-ups, I believe, telling about the use of not liquid helium, but actually of helium itself in wind tunnels. Now, how does that work?
Yes, about 5% of all the helium used last year was used in wind tunnels. In wind tunnels, they want very high velocities, and you can get that easier with a gas that has a low viscosity like helium than you can with air or other gases. Another thing, if you use air, the object that you're trying to test in the wind tunnel might burn up, whereas helium, as we've seen, is chemically inert and so does not react with any of the objects that are being tested.
So then we have a space simulator, and we have the use of helium in wind tunnels to simulate, again, conditions at great altitudes and in outer space. But we can also, I know, use helium down at the bottom of the ocean, and to introduce that, we should look, first of all, at the standard diving helmet, which is good for, shallow depth, shall we say. But if you want to go down real deep, then you have to use this kind of a helmet, which is the helium hat. By use of this, then the diver can have a helium mixture. Now, I know you people have been doing some work studying the physiological exchange rate of certain gases such as helium in the blood. And how does that work?
We found that the solubility of helium in blood is considerably less than the solubility of other gases. Now, if a diver goes to very great depths where the pressure is high with ordinary air, the nitrogen from the air gets dissolved in the blood. Then it takes hours to bring him through the decompression chamber so that he won't get a very painful disease called the bends.
Right.
But if he has a helium mixture, then in the first place, the helium is not nearly as soluble as nitrogen in the blood, but also the helium comes out of the blood, the little bit that did dissolve, much faster than the nitrogen, so the decompression doesn't take nearly as long.
So then the time that he would spend coming up from the bottom from a deep dive then is cut rather radically as a result of this helium mixture.
Yes, and also the risk of his getting the bends cut way down.
Now, Gerhard, let's go over in this next section and talk about the future of helium and these other rare gases, and also discuss this field, cryogenics.
Yes. You know, Earl, cryogenics is a science of low temperatures, and there are some interesting cryogenic applications of liquid helium. One of them is the superconducting magnet. There are some metals which, when you make them into wire and pass an electric current through them, there's no resistance at all, and the electric current keeps going forever as long as you keep the wire cold. You can wind coils from these wires and make magnets that are very powerful.
Sort of a perpetual motion machine.
That's right.
Could you apply this same principle of working at very low temperatures and gaining great efficiency, could you apply that to the transmission of power along an electric cable?
Yes, we think you could. It's never been done yet, but we are making calculations and working on the problem. Recently, a large new hydroelectric plant was opened in Niagara Falls, and I visited and saw these hundreds of cables going out in all directions carrying this power off. And we have calculated that one single strand of superconducting wire in a 2-inch cable could carry all that power to any place in the world that you could keep the cable cold.
You know, earlier in the program, in fact, when I took chemistry, I learned that all of these elements down here, starting with helium, were inert. And yet, in our discussions earlier today, you told me something, I gather, that's going to change all this.
Yes, when I wrote the book, I thought all those elements were inert, and the book came out in 1961. In 1962, an announcement was made that really startled many chemists, including me, and that was of a stable compound of xenon. Since then, a half a dozen other compounds have been announced. One of them is a very simple compound of nothing but xenon and fluorine called xenon tetrafluoride. Looks just like powdered sugar. It's perfectly stable. It'll probably last forever as long as it's kept in a sealed bottle.
What happens if you take the top off?
If you take the top off, moisture from the air gets in and changes it to a compound called xenon trioxide, which is unstable and which explodes with very little stimulus.
May I return this to you? You know, from the things that you've described here during our program, I can see that the future is a very thrilling one, certainly for this group of elements beginning with helium that we've described here. I want to thank you, Gerhard, for coming out to be with us on the program.
Well, it's been a lot of fun, Earl.
Thank you. Our guest has been Dr. Gerhard Cook, and he comes to us from Tonawanda near Buffalo, New York. His job there is assistant manager of the research laboratory of the Linde Division of Union Carbide Corporation. And of course, he's told us about many of the thrilling events that are taking place in the research field dealing with helium and with all of these other elements indicated in the first group: helium, neon, argon, krypton, xenon, and radon. Well, that's the group, and we hope you've enjoyed it. Now, don't go away, because I'll be back very, very shortly with the Animal of the Week. One of our country's most protected animals is a large, grotesque, and ungainly fellow, the elephant seal. Many years ago, there were large herds of these animals along the Pacific coast, but they were killed off in commercial sealing operations until in 1892, there were only a few animals remaining. And today, due to protection, there are about 10,000 of these elephant seals, and they are found in an area along the Central California, Southern California, and Baja California coastline. Now, one place where they really congregate is at Año Nuevo Island, a short distance south of San Francisco. Now, on this 9-acre plot of land, there are a great number of these animals. Formerly, this was a lighthouse station, and it's now under state jurisdiction and is being held as a research preserve. The reason is obvious when one considers the data amassed by Dr. Thomas Polder of the Stanford Research Institute and Dr. Robert Orr of the California Academy of Sciences. As many as 8,000 seals and sea lions of 5 different species have been counted on this small island at one time. Year-round, about 500 of these are elephant seals, the males of which are easily recognized by the giant nose. A full-grown male may measure 18 to 21 feet in length, 5 feet tall at the shoulder, and weigh as much as 3 tons. Females and the immature animals lack the elephant nose. The females measure 9 to 11 feet in maximum, with a weight of around a ton. One of the hazards of working around elephant seals and sea lions is that they may object to the photographer, and although they are awkward on land, they can still travel at a speed of about 5 miles per hour. One phase of the Año Nuevo investigations deals with the geographic movements of elephant seals. A large hoop net thrown over a youngster, and I say a youngster advisedly because they may grow at a rate of 15 pounds per day, enables the animal to be immobilized so that a special tag can be attached. Thus, future movements can be recorded as these individual animals move to and from the island. The pups are always the most attractive, and this young stellar sea lion pup is merely being friendly as he attacks Dr. Polder's pant leg. But as he receives a bottle of special food, everything is all right. Well, that's it. The elephant seal and about 6,000 other seals and sea lions at Año Nuevo Island. We hope that you've enjoyed our presentation, and we'll look forward to seeing you on our next program. Thank you very much.